So, anybody saw Irishman yet? How did you like it? Um, Seems to be a really important and cool movie that we just released. So we'll start this talk by a tweet. And the tweet goes like this. Gradient descent can write code better than you. I'm sorry. Now, how many of us here still remember what gradient descent is? Just a quick show of hands. Okay, so that's great. For those who are, I'll bring you up to speed. Gradient descent is the first derivative of a mathematical function, something we call похідна. And if you follow that in the direction of a steepest descent, you can arrive at a minimum of a function. The beauty of that is that you don't need to know the function. You can do that numerically. Just by calculating that, you can arrive at a minimum. And if the function happens to be the cost function, you can find an optimum for a problem. So this way, you can do statistical models. If you optimize them to a minimum, you find some sort of an optimum. And that's great. Now, how many of us know this guy? Okay, well, we'll talk about him. We'll talk about him and you'll learn more. Now, the topic of this talk is from encoding to machine learning and the way infrastructure evolved at Netflix. Despite that I claim that gradient descent can code better than you, there won't be too much of the code. There will be more of an architecture and more of a philosophical discussion. Just heads up. So why you should listen to me on this topic? Maybe because I made my first 100 steps to EPAM. But maybe because I moved on. I was one of the first engineers at Grammarly. And then from there on, I started doing more and more media and media systems and media analysis at companies like Sony, and then at Twitter, and then I was a tech lead at Pinterest, and eventually I ended up at Netflix. So my name is Arsen Kostenko. I'm a team member at Media Intelligence team at Netflix. And media intelligence is kind of, very broad topic. We don't try to build the artificial intelligence. We don't try to build the general artificial intelligence, nothing like that. Our charter is much smaller. What we try to do is understand what's happening in the video. Simple as that. Well, it started simple. It started from a really simple things like file checks. Any media pipeline out there has a step called ingestion. That's where the media arrives to the platform. And at that point, you want to make sure that your file is correct, that the file is there, that the file is right format. So we had these, this portion of the system that was doing these checks. But eventually, it was a natural place where we started thinking, hey, maybe we can place there some more things like, let's look into the video. Is the video the right format? Is the format structured correctly? Like, is that matroska or MOV file? What type of things we need to do now so we wouldn't have more headache later? And eventually, one by one, we ended up in a place where we started not just checking for a file, but looking into the actual frames, actual pictures, and figuring out what's happening in there. We started adding more information to the pipeline than just, preventing the future fails. Like, one good example of that is dead pixels. So the problem with dead pixels is that movies are made with the cameras. And cameras are physical objects. And physical objects have physical defects. Here is a small example. What you see is that there are places in a video where the color information is very little. Essentially, pixels that don't change with color with the time. The problem with this is that the more you encode the video, the more these guys tend to stick and they grow. You can think of that as a tumor of video encoding. So the source of this could be different. It could be a broken pixel on the metrics of your camera. It could be some dust. It could be some physical damage, whatever. The earlier we know about them, about their existence, the earlier we can push back and make sure that the quality of the video is great. Another interesting topic that we try to solve is product artwork. So let's talk about Netflix. When you arrive at Netflix, you see this list of movies, what we call Lolamo. And then on a Lolamo, you see pictures of some of our movies. Those movies are like a fraction of the catalog. And now, the interesting part about that is that we need to pick out which portion of the catalog to show you. That's a classical problem of matching user to a content. Now, this is usually done by search recommendations. So we look at your history, we figure out what you watched before, we figure out what people like you watched before, and then we recommend you things that other people watch. That's like a gross over-exaggeration of the recommendation system. But there is more to it. So there are multiple options to pick for an artwork. So we need to pick one of the multiple. One for a movie. Well, that's fine. Maybe, the catalog is a couple of 100,000, but you can still, go through, pick one for each movie. That's fine. But then the people come, and people make everything really, really complicated in the sense that I tend to like different things than you, and probably one of you. So what this means is that we have this triplet. We have a movie, a person, and a picture to show them, and we need to figure out the right combination. So this kind of multiplies the problem. You have movies times number of watchers, probably times number of options that you have there. But that's not it. There are also more and more and more pictures. You have to make that decision every time. Now, the question is there, could we somehow let the computer take the movie and tell us which frames in that movie are beautiful enough to become potential artwork? Kind of superpower the humans. Now, the tricky thing here is notion of beauty. It's subjective. So we try to build a tool for our operators that can go through a movie and figure out a nicely formed image out of the movie frame. Another problem that we are dealing with here is a banner selection. That's very like the previous problem, but this time it has a little bit of a structure to it. So it's not just a beautiful picture, it also needs to have a certain logical layout. There has to be this big, vast space that is just beautiful, but there also needs to be a place where you can place some text so people could read it and some controls, and there shouldn't be anything important down here because you don't want to cover the important pieces. So it could look like this. You see, there is a boy, you can see him clearly, he's not blurred, but then the other things on the left here, they could be blurred. That's okay. And the play buttons are clearly visible, so you have all this. And there is like no monster jumping out from down here, no face down here, so that's also important. But that could be reversed if you are watching it in a different script, different language. So all these things need to be accounted for. Now, the last portion of the thing that we're dealing with is a QC. Essentially, we need to make sure that the whole experience is great. Now, one portion of the QC is the production QC. Here, that red rectangle on the far left is actually a camera or a light. And it could be okay if this was like a movie about cowboys and aliens, but in this case, it's not. So we need to figure out the way to, help our producers see this object and go like, this probably doesn't belong here. So they could make the decisions faster. Finally, the other part of the QC is the user QC, the streaming QC. The QC you see when you want to be as close to your user as possible. So here the problem is that text is really hard to read when it's overlaid by something else important. you have a name of an actor overlaid by subtitles. And it's clearly a bad thing. When you see it, you know it. But like, let's step back and figure out, what do you actually need to do to find this problem? If we had humans, most likely they would have to watch all of the movie with all the subtitles just to spot this one place. For computers, it's really easy. If you give computer 2 different rectangles, they can figure out where the rectangles overlay, voila. Now, the tricky part is, how do you make sure that your algorithm that finds out the text does the very same thing as the algorithm that figures out where the subtitle is going to be shown? Well, I think this last example is kind of highlighting, but overall, you see how we are keeping doing more and more computer vision. Even though we started with encoding, we're doing more and more computer vision, and that means we need to talk about machine learning and how these things are done, because machine learning kind of took over the industry. Now, important thing that happens is when you go from academia to industry, you usually have this, change. In my high school years, in my university, I used to obsess about algorithms and about new neural network architectures. And you just come up with a new thing, and it's going to be great, and you're going to solve all the problems. But in reality, I lose most of my sleep due to data, taking care of the data. The interesting thing here is that back in 2012, I tried to build this first neural network to do the subtitle match. It could detect the burned-in text in a frame. And that's really nice. But when I presented that at one of the meetups, a guy stood up and said, why don't you use recurrent neural networks? They are vastly superior to anything that multilayer perceptron does. And I was like, yeah, that's right. But I just spent like 2 days just trying to come up with a data set for this. There was nothing before. So the thing is, this is not even my slide. The original slide looked like this. So we're talking about difference about PhD and Tesla. And the guy who put that slide up is this guy, Andrei Karpathy. He's PhD at Stanford, which is a really good university, if you happen to be computer science or something else. But he's also a director of AI at Tesla, and he was a researcher at OpenAI, one of the very respected AI institutions. And let's ask ourselves, why coming up with the data is so hard? Well, one of the reasons is domain shift. Domain shift is this problem where you collect your data set in one particular environment, but then certain biases about that environment creep in, and your model is optimized towards that. And when you roll out your model to production, the actual data happens to be different. In this particular example, let's imagine that you collected your data set by walking the streets of Kyiv, and it was great. But then when you deploy a model to production, it turns out people drive at night. That's surprising. And suddenly, your data looks very much different. It could not be just day and night. It could be like, let's say, a sunnier days in California versus more gloomy days in Berdichev, or something like this. It could be, you install your camera in your machine, in your car in one way, and then when you sell that setup to a different manufacturer, they install the car at a different angle, and it completely screws everything up. And this problem was known way before. Like the first wave of AI, when they came up with the perceptrons, and there was this guy, maybe Marvin Minsky, who completely destroyed the field by just saying that perceptrons cannot do XOR operation. They're really good at AND, they can do OR, but XOR is like far beyond their reach. This caused the first AI winter. But then he also went on to say one more thing. What actually those perceptrons were learning is the amount of light in a picture. the first thing where they tried to employ that was telling the difference between a tank and a truck. And it turned out that tanks were pictured on a sunnier day than trucks. And that's everything it did. Now, this goes far beyond. Right now, we're a little bit more robust than that, but this goes beyond this. So this also is known as adversarial attacks. You have a picture, you add some noise to it, like seemingly random noise, and then suddenly your panda becomes a gibbon. And that's like, this is a real research proven, and this is what is happening in practice. Now, at this point, let's have a game. Here are several pictures. This one is like one from a data set. The others are pictures that were printed on a physical printer, on a paper, then pictured with the general, smartphone. And now we try to classify those pictures. Let's imagine ourselves the developers. We're building an app. Let's call this app Держава у смартфоні, just for the sake of the argument, And now let's see what happens. So what do you think is the confidence of our neural network on this first image? Well, it's our data set, so it should be 1.0. Yeah, we're pretty confident that's a washing machine. How about this one? Okay. It's close enough. Close enough. Not perfect, but close. What's about the other one? 1.3. 1.3, 1.31, 1.32, 0.3. Okay. 0.3 solved. Now, in actuality, it's mostly a safe, not a washer. And just a little bit of washer. So the confidence on the washer is lower than on the safe. What's about this one? Okay, well, could be something else. In actuality, our network predicted that it's a safe or a speaker with a lower confidences than any of the washers before. So, generally speaking, how do we deal with this problem? Well, we add those examples to our data set to train our model once again, to make it more robust against these attacks. And sometimes we manufacture those attacks ourselves just to make sure that the data is robust enough. What does this mean? This means more infrastructure. More things, more services have to be put in place just to make sure that our model doesn't screw up. And here is the paper from Twitter back in the day when they were trying to come up with a machine learning infrastructure. What they noticed is that practically you need a dedicated role that makes sure your infrastructure is there and your infrastructure is up to the par to match the correct input to the model so that your input is not too much different from what your model is expecting. Well, here is one more paper. This one is by Google. Google was doing the statistical models for over 20 years now, and it means that they know quite a bit. What they say is that there is an inherent technical debt to any machine learning, which means you're going to be putting more and more services out there, and you will be deprecating them over time. They go on to say even more things. They say that if you try to embark on this journey of machine learning and AI, there are going to be way more services, way more code, way more things have to be put in place, and your technical debt will be increasing much faster than you can expect. An average machine learning setup will look like this. So this is just to make sure that your model is there and it's working correctly as you expected. One of the biggest problems out there is that when it doesn't work correctly, it's silent. It's not throwing you exceptions. It's not showing you 404s. Services are still up and running. What happens is your business metrics start to decline. Sometimes they start decline not like the primary metric, but the secondary metric. Sometimes it's declining over a longer period of time. So you need to know when exactly to look at what. And you need to be actively looking for those metrics. Otherwise, you will not see this. At this point, you might think, okay, but there will be a state where we will know that our data set is robust enough, so our machine learning model is robust enough, and we can, proceed and remove all the extra tooling. Well, at this point, our friends from Edison Horowitz come back and say, well, it might not be the case. Data gets stale. Sometimes, if we take our previous example with automated driving, streets change. Like streets here in Kyiv are very different in spring and autumn, precisely because there was winter in between. Sometimes the paint can be gone. Sometimes the pavement itself can be gone. And you still need to direct your car and understand that that's essentially the same street. You put a crew of workers on the street, and the street is already different. You need to be cycling the data. You cannot have it in one place just for the sake of it. So not only it's harder to get new data, but sometimes to get new data, you need to pay more. You need to get to a place, let's say you have some strange street to which not too many cars go. So you need to dispatch a specific courier there so he would make pictures of that. It costs you. Not only that, the additional data will bring you diminishing returns. So you don't want to invest in that too much, which means you will be cycling your data set a lot. Essentially, this could be summarized with these words. If you think that your data set is your competitive advantage, you are wrong. Competitive advantage is what moat means in here. So a good analogy that I really like is that if you think of machine learning or your model as your binary executable, then suddenly your data set becomes your code. And if that is the case, then your GitHub is your data infrastructure. We all know that if there is one thing about the code, it's that it keeps changing. You cannot have a perfect code. You need to be working on it. This means that your data infrastructure might be more important to your company than your data itself. And when we work with this, we currently ask 3 questions to our code. What changed? When it changed? Who changed it? And why? Do we have answers to that? With the data? Not always. But if we don't have those questions, how can we make sure that it actually is doing what we want it to do? Well, we need a system that has at least these 3 properties. It can tell us exactly what happened at a particular point in time, so a snapshot view. It has a commonality extracted so you can somehow reason about it. And it has accountability to change, so you know which change was made by whom. Okay, so we glanced over the machine learning landscape. Now let's go to Netflix and try to solve this problem. We're doing more and more computer vision, which means we're going to be doing more and more analyses. Now, every team is going to be storing those analyses in some form. And if we don't act proactively, it means that eventually we'll be combining different formats between different machine learning tools, because usually the output of one machine learning prediction becomes the input to the next one. So if we don't act now, it means that eventually we'll be in a mess where there are incompatible formats and incompatible things that we need to somehow marry together. How would you solve this if this was your company? That's the question my manager came to me first when I was given this task. How would you solve this if that was my own startup? Well, let's go from the beginning. What do we see here? A nice picture, but it's also moving. And we know that there is a boy on the left rightish, there is this mountain arc kind of thing, top there, and we probably don't have much of information in the corners where we maybe can place that Netflix logo in there, but there are also these fireflies flying, so there is some spatial information and there is some temporal information, time and space. Well, if we're a startup, we usually do things fast and cheap with the duct tape. So we put sticks and duct tape, and I don't know how it's for you, but for me, the duct tape is the JSON. So I would put this JSON structure. It has start time, end time, and then 2 coordinates which denote the rectangle. And with this structure, I can maybe encompass some information about that in the picture. Well, would be nice, but doesn't really work. Why? Because video is not just that. For video, the time of a sound is different than the time of the picture, called frame rate and sample rate. Not only that, the time for the subtitles is completely different too. And you need to, capture the information when the subtitles is shown as well as sound. Okay, but it gets even trickier. Sometimes your picture can change its frame rate in the fly. Sometimes you have, one frame rate for the first 10 seconds and then different frame rate for the next rest of the movie. Okay, so this means we need somehow to encompass that. All right, fine. It doesn't end there. There is a spatial thing, as we mentioned. So you need to have a rectangle to denote a face, but you also need a place where to put a subtitle. So you need some way to describe space for your subtitles. And you would be surprised, but sound is also more and more modeled as the 3D structure, like a Dolby Atmos thing, where they have sound not encoded as the one thing in time that is projected out of speakers. It's an object emitting the sound in a 3D space that is then somehow adjusted by your particular setup. Like you are at home with a 5.1, or you are in a theater with a 64 speakers, it all gets modeled differently. Okay, so we have all this complexity, nice. Now, let's go and talk this through. We have an asset. An asset is going to be composed of a number of tracks. Tracks are going to be those horizontal things that we just saw. Then track is going to have its own metadata and some details about it. And the details are going to be components. Components are essentially those collections of different sample rates within the same video. Okay, that's nice. Then we have our events, the points in time where something is happening. And then eventually, event has its own details, and it has the region which is the spatial one. Okay, so now we kind of arrived at something. The last time I gave this talk, a version of this talk, feedback was there is not enough of meat, which I took as there is not enough of JSON. Here is more JSON. So we'll start modeling just as before. We have point 1 and point 2 that are going to be describing the rectangle. We have some metadata. Then we have our space. We have start time and end time, and some metadata to that as well, which is enclosing those regions. And then finally, we have component that has the spatial information and temporal information in that, as well as some extra metadata. And we have tracks. This time components are inside this thing, and then we have our assets. So all this becomes descriptive enough to at least capture like 80 to 90% of your video. So you can finally pinpoint a point in a frame. Nice. Well, kind of describes everything, kind of looks good. Yay, we did it. Now, there is, of course, danger looming behind. The problem is our serialized JSON looks like this. It's a one huge gigantic string that we put into our database that we have no idea how to process. And you can blame it on the JSON, saying it's all about, the attribute names. Let's extract them. Let's use different schema like Avro or Proto, and it will be smaller. Let's zip this JSON. This is not just a problem with that. It's the problem with the content size. Our movies tend to get longer and longer, and this one is like 3 hours. The other one is multiple storylines. Have you seen that one by any chance? Okay. So in actuality, there are multiple storylines, but all of them need to be encoded. It's just really, really increases the time of the movie. And the last one is for kids, but the idea is you have multiple characters. That could be a boy, or look at that, a girl. And suddenly, it could be not just two characters, but maybe there could be a puppy, a kitten, a unicorn. And your movie just became 5 times longer. There's just going to be more data. Okay. So not only that, we also know that everything is a microservice. And in microservice, world looks like this. It's all moving. It's all at once. And if there is certain thing that is going to happen, it's this. It's going to be a failure. There's going to be a partition, and you need to be engineering towards that. This is sometimes presented as the CAP theorem. So you have partitioning available and consistent, but this is a misleading view a little bit. Partitioning is not something you have control over. It's forced upon you. It's the fact of the world. The only real, flexibility you have is being available or consistent when partitioned. Like, how many of us understand what partitioning is? Okay. So, if the failure happens, you can be very available. You can accept, like if someone is storing a write to a database, you can always accept it. Just talk to one node out of a cluster, and this node will say, yeah, nice. The problem with that is if that node happens to be the one that failed, your data is lost. So you're not really consistent. Well, you can improve that by doing local quorum and a single data center. Then you have to write to more nodes, and then hopefully your data will be more safe. But if partitioning will happen across data centers, it will not work. And you have a global quorum where things will be stored in multiple places, but then it's really hard to be available all the time. It's much more likely that you'll have 404s and rejections from your database. Well, knowing all this, what would be the simplest way to do things? Well, you're going to have your client that will talk to a service, and the service will go to some storage like Cassandra, to Elasticsearch for indexing, and will save everything to S3 because there's just lots of data. It cannot fit into Cassandra or Elasticsearch on alone. Okay, and then you'll get your result back. You are read after write consistent, great. You have your ID, everything's magical. But there are many things that will go wrong here. Like if the data is that big, very likely that it will just fail between client and the server. What if it fails not there? What if it fails like during saving to S3? Then you have some metadata in Cassandra, you have some Elasticsearch indices, but there is no actual data to get back to. So you need to make sure that everything works together. Now, we are engineers, and the way we usually do things, we complicate them. We hide the imperfectness of the real world with more complex systems. So the new complex system will look like this. You have the client, you ask the client to store things to S3 first. Nice. Then you go to your API and say, save this information from S3. Nice. And then it will go to the conductor, to some kind of a workflow orchestration thing, which will, in turn, move on and say that the request is passed down to the client. Client can now wait for the request to be processed, and our storage service can come up, and the storage service can get the data from the S3, write it to Cassandra, then get a reply, and finally we are read after write consistent. From this point on, client can move on. If there are some clients who are interested in indexing, they can expect our eventual consistency once the indexing service is done, and then we're good. So all this complexity was needed just to hide the internal imperfectness of the world. And we finally could be happy. Okay, this is fairly usual setup. This is how you do things in a world with failing things. But again, there is a danger. The danger this time is that this setup is popular. It will probably work. But also because it will probably work, different teams will build different data formats on top of that. Remember that media document I talked before? All of those parts had this thing called metadata. And the metadata is going to be different for each and every team that is owning different inspection. Like, I don't know, face detection team and audio analysis team, they're going to come up with the different structures. Let's take a look at the region example. So here, the metadata is just one single integer, a confidence. It's nice, but the next team might be interested in some kind of a categorization. And they might have need for a category of series of integers or real numbers. And then to denote different categories they are interested in. And this kind of makes the structure different. Well, we can mimic this with this protobuf structure. So you have a point, which is classical, and then you have a string where you serialize your JSON. And this works, but it kind of makes indexing really, really tricky. It makes it much more hard than if you could build the indices up front. All right. You can do a struct, and that will maybe make things a little bit better, but you still don't have any better insight into what the metadata is about. Eventually, you will arrive at the state where everything is a mess because you are still marrying different formats and trying to understand whether that's an array of integers, a single integer, maybe some other complex structure. So what do we do here? Well, we ask users, we ask our customers to provide us a schema upfront and tell, well, my metadata is going to be different. My metadata is going to be structured exactly like this. So every time the data arrives, please check for this. This is what is called a schema on the write, as opposed to schema on the read for the NoSQL. For the NoSQL, you just write the data into the database, and then when you read it, you try to reconcile this. In this approach, you essentially confirm the data to a schema, and then eventually, if it's not confirming, you reject the write. Yay! Finally. But now it means that all of our system looks like this. You start with the client, you go to the API service to declare your schema. Then you go and store it. Then you go and issue a store request. And it keeps going with the more complexity. You are waiting for the request. You have the validation service, which will actually use your schema. And then that validation service still needs your S3 to validate it. You go and confirm that. You go to the storage service, which can finally get your metadata and store it into S3, into Cassandra, I'm sorry. And then from there, you have read after write consistency, which is still good, and you have an indexing service. Wow. That was really a lot of management for a really teeny task. Essentially, we added all this complexity just to make sure that things will go badly in a more predictable way, that we could capture them when we needed to. So what we arrived at is a system that has a snapshot, this big media document. We know what's going to happen in there. It has the common format, so we can cross-correlate differences between, say, team that is doing the subtitles and the team that is doing audio. And we also have an API access where we know who changed and what. So, okay, what does this mean? Let's decompress a little bit. When you're doing the machine learning setup, your machine learning is going to be about data. Think of data first and your model second. It will arrive, the model will be found, it's going to be fine, but make sure that the data is there and the data is up to your standards. And when you think about the data, the first thing you need to be thinking of is your data collection system and monitoring of it. If you ask me for one single advice, I would say this is the book. It will not give you answers, but this book will give you questions that you can ask your customers, yourself, and your system, so that you know what compromises you're willing to make and where exactly you're willing to make them. Now, wait a second. At this point, you can be going like, Arsene, so you started with this assumption that gradient descent is better at coding than I do. And then you went for 40 minutes ranting about how hard it is, how bad it is, and how complex it is to achieve this. Let me use Andrei Karpathy one last time to kind of summarize this. In the previous world of software 1.0, we were writing code to solve one particular problem in one particular space for a known data. We might be arriving to a place where the data is the way to make a decision. And the way to do this is to describe it, like describe all the possibilities, and then let the gradient descent figure out the solution. It might be easier in certain cases. So to wrap it up, let's formulate it this way. Gradient descent can write code better than you do. And you need to make sure that you try really hard so it really, really does. Thank you. Here are some references, and I think we have some 8 minutes for questions.
Thank you. You mentioned you have a workflow-based system. So when you upload the data, you start a workflow and running the processing against several services. So how do you handle failures? For example, if something fails when you're writing to Cassandra, do you have any retries?
So, yeah, thank you. Usually, we handle that by adding redundancy. So every single box you saw there is actually a fleet of nodes. And all of them are, deployed using Kubernetes or something else, so that you actually have a single point of entrance, like a one command line interface, where you deploy something, but behind that there is load balancing, there is routing, and there is all this. That's like almost given to you.
Thank you.
You're welcome.
Can I answer this question? I'm not on your project, but you showed like Conductor, for example, right? And Conductor is like workflow orchestration system that supports like fault tolerance out of the box. It will retry for you. It will like keep like, if like write to Cassandra fails or something like that, it provides this functionality. So it's all, yeah, it's like infrastructure is very comprehensive. But Conductor, for example, is open source. You can use it.
Thanks for the presentation. So in your presentation, you showed that basically future is about working with data and gathering the data, injecting from something, for somewhere. Do you have, and also in the course of presentation, you talked about perceptrons and your first problem initially, long time ago, when you have problem gathering the data. Do you have any suggestions or like solutions to like how or approaches to gather data for concrete problems, like, or it's really ad hoc approach usually?
Yeah, thank you. So there are two things. Not all problems can be solved with data. Some problems humans are amazingly good at, and you need to know how to pick your problems. Usually, if you think of a problem that is, it has lots of rules. If your code has lots of if and else cases, and somehow it's like it starts looking like a rule engine, that's the place where you should be start digging. If you look at the inputs to those if statements and those conditions, most likely you will find some sort of a structured or unstructured data, and that's where I would start. Now, collecting your first data set is really tricky, and that's like where lots of research is being focused. There is some promise in synthesizing your data, but then again, it depends on the problem. We can talk offline if you're interested. All right, thank you.